Good afternoon, everybody. I got my voice back a little bit. So, a couple quick announcements. First off, if you missed the recording yesterday, we opened Canvas Quiz 6. This is your final scored Canvas quiz. Instead of being due on Friday, it's due on Thursday. So one day earlier, that way you don't have to worry about it on Good Friday. So try to get it done for 5 p.m. on Thursday. This is our final scored one. There will be one more quiz that's going to open up just for practice right after this one. So it'll include all the Deals Alder content, everything else is practice material for you guys to do for the final. If you haven't already looked at the calendar, we've got those classes left today and Wednesday. That's the goal that we're trying to target in. So last class for content will be on Wednesday. That gives you everything else free, no class time leading up into your final. No clapping. But the point is, that way we can finish on that material. What I'm going to try and do is put together anything else for review material. I still owe you guys a walkthrough video for midterm 1, have to write that one, and a walkthrough video for midterm 2. Both of those will be posted up, so you've got sort of like a point-by-point for how these questions get executed. Just a quick note, I will have your final grades, everything else from midterm 2 by Wednesday. At the moment, we still have to do the bonus question, but we're already sitting higher than 65 for our midterm average and stuff too. Again, I need to go through the last parts of it. Just please be patient on that part too. Last notice too, for CFA students, our final exam is set. It's noon on the 15th of April, and it's going to be at SRC, so do book your bookings. All right, so last class, we talked our way through Deals Alder reactions. These are the first 4+2 cycle additions. Now they're special is what we're doing is taking two planar rings and we're bringing them together in a very specific geometry. Molecular orbital overlap is what's giving us basically forming 4 chiral centers with really, really discrete control. And it's because we're taking these two flat systems and the pericyclic reaction requires a certain outcome for your geometry. And we walked your way through 3 different levels of stereochemistry you should know about now. So there's enantioselectivity, which is your top and bottom. There's your diastereoselectivity, that's your endo-exo, what's your basic, how your dienophile is approaching your diene, in or out. And then you have your regioselectivity. So this is kind of top and bottom, or basically looking at the two as either polarized or antipolarized relative to each other. So I've gone through examples of those. Those are in the past couple of lectures. Please do go through those 2 parts. I've also given you guys a template or a mnemonic. When I was first learning this, it's really difficult to spin these in 3-dimensional space. So I've created sort of a general template saying if you can line up your groups in these particular positions in your diene, your dienophile, you will see programmatically where top face and bottom face geometries were laid out. So do practice that part. If you're having any issues with it, your 3D models are really helpful in this part too. So quick review. This is your starting material. There's your product. You're going to get an enantiomer of it, but you get this specific geometry. What is your dienophile? Take a second, work backwards, add these 2 pieces, and do the disconnection to see what your piece is missing. Okay, so let's do this decomposition here. First of all, any Deals Alder reaction, there's a really clear hallmark core that you're making from a Deals Alder reaction. What is it? What's the name of the 6-membered ring you are forming from a Deals Alder reaction? It's always called a cyclo. How many atoms in your ring? 6-membered ring, so it's a cyclohex, and usually it's going to have a double bond. You are making a cyclohexene. So if you look at your product, the product of your Deals Alder reaction is this core right here, that double bond in place. Now if you look at your starting material, let's number out the carbons. I'm going to start here. Carbon 1, 2, 3, 4. That's my diene. If I look at my product, the center with the double methyl, that's carbon 1, 2, 3, 4. Remember, any Diels-Alder reaction starts on the diene side. Bonds 1 and 2, 3 and 4, those are your double bonds. Your product between 3 and 2 is your new double bond. It shifts over by 1. There's new sigma bonds attaching to carbon 1 and carbon 4. So that's how it's mapping out. And again, if you look through it, carbon 2 has your ester, carbon 3 has a methyl, carbon 1 has your dimethyl. So that's that center. That means this is your new bond, this is your new bond. Your dienophile is this junk over here. So the dienophile is always going to be an alkene, right? That's your core center. That's going to be your carbon 5 and carbon 6. And over here, that would be carbon 5, and right there is carbon 6. Based on how we broke this out, carbon 6 has two things attaching to it, a chlorine and a cyano. So CN and chloro. So that would be our dienophile. Now again, remember what we called this too? There's two kinds of Diels-Alder reactions, or at least when we talk about this. The diene is usually what? Has electron donating or electron withdrawing groups. Diene usually has, in our normal Diels-Alder, diene has what? Donating or withdrawing? Donating groups. The dienophile has your electron withdrawing groups attaching to it. So that matches. If you look through this, my donating groups are things like the methyl. This oxygen here has lone pairs that can actually donate via resonance, versus the dienophile, nitrile, is electron withdrawing, chlorine, electron withdrawing from a sigma skeleton. So that maps out of this part. Last time we talked you through why you would get this regioisomer. What I mean by regioisomer is where these two groups land up. If you look at this pairing, I can do this like I've drawn out here, carbon 5 and 6 matches this way. There's also a possibility to have the other regioisomer. I take the CN and chlorine, what I've labeled as carbon 6, and I could flip it over. That's still a Diels-Alder, everything's kind of lined up. This is where you should be able to go through this decomposition based on the resonance structures, where the polarization is, and prove that this geometry I'm showing you here is the favored one. That's just as a result of where the groups are on your diene and your dienophile. Okay, what we're going to talk through today is the inverse demand Diels-Alder. This is where we're switching the polarity. Remember, when we talked this one through, the normal Diels-Alder, the highest occupied molecular orbital of the diene, the thing that has the donating groups on it, and the lowest unoccupied molecular orbital on the dienophile is usually what you're bringing together in terms of your molecular orbitals. If we switch the electron donating and withdrawing potential, we're just switching which orbitals get involved, but it's still allowed. What we're doing is we're just taking what normally would be at different levels, bringing down the LUMO and bringing up the HOMO in order to get them to react with each other. We're also going to talk through the last kinds of paracyclic reactions. These are sigmatropic arrangements, what we call the Cope rearrangement, and the Claisen rearrangement. So first, inverse electron demand Diels-Alder reactions. What we get is still a diene and a dienophile. What you look at is different here is look at your diene. Instead of being a system with a lot of donating groups, often we get these diene-like ones. You start to see heteroatoms in them. So this is where we can take a normal alpha, beta, unsaturated system, in this case like this aldehyde, that's effectively being our diene because it's still 4 atoms, 2 pi systems acting as part of our fragment. And then the only way this is possible is because what we've done now is we've inverted where the groups are. Here, this is really thought of as an electron withdrawing group. Remember, there's a delta plus sitting down here in this point here. So this is usually an electron poor diene now. It's no longer a fully carbon one. We have this heteroatom in the place. And if you look at your dienophile, we have this lone pair attached to this oxygen. This is going to be donating electron density into our pi system. So we've just taken the polarization we've normally used to, and we flipped it. The dienophile has our electron donating group. The diene has your electron withdrawing group. That allows it to happen. So this is where we get that pairing. You're not going to get a case where the diene and the dienophile both have electron withdrawing or both have electron donating. They're going to have this opposite polarization in some way. So if you're going to get something that looks like this, a heteroatom acting as our diene type system, your dienophile has to have a strongly electron donating group associated with it. No chlorines. It's going to have things like O-methyl or multiple O-methyls associated. But in the end, you're still going to make something that has 1, 2, 3, 4 atoms. That's these ones. And still making 2 new sigma bonds here and here. And you have your final 2 centers, 5 and 6, which are carbons 5 and 6. Still pericyclic. Geometry still plays the same way. Everything else in terms of the regiochemistry that we talked about still applies. The only difference is you've just got this opposite polarization for where the electron donating and electron withdrawing groups are. This is an EDG at this point. So the last kind of Diels-Alder, and what's most important for these inverse electron demand Diels-Alder reactions, is what we call gas extrusion. So what we're doing here is, if you look at these, all of these are actually diene-like. They don't look like our typical ones, but this is why we use them. These 3 are your very classic ones, what we call gas extruding Diels-Alder systems. Now, if you look through each of them, why this works is we've got a relatively electron poor diene. They've got electron withdrawing groups attached to them. And the way they work is you're going to do a cycloaddition, but remember we had a couple examples of this. If your diene is already kind of tied together on the end, so something kind of like we showed you examples of dienes that looked like this. This is a case where that is carbon 1 and 4. You're adding a cycle to it. Because they're tied together, you end up making a bicycle. It looks like a little house. That's what these ones are kind of like. Each of them is already a cyclic system, which means carbons 1, I'll show you on this one here in the first. This would be carbon 1, that's carbon 4, 3 and 2. So that's the diene portion of the ring, which makes this my CO2. We're going to do a cycloaddition, which will make a bicyclic structure. It's going to have this bridging structure. Now, good news is we can form it, it's allowed. But how these reactions work is by having that sort of molecule of gas tied up in the system, we can do another cycloaddition which kicks that CO2 out and locks in your final product. So it's a 2-step system where we use these molecules as a diene. We make these bicyclic structures, but then the way we get them onto product is by kicking out some molecule of gas. So the one in the middle, their CO2 is designated there, where the green atoms are my diene. Over here on the end, this is my carbons 1, 2, 3, and 4, where the atom I'm extruding is actually SO2. So that's my SO2 being released in this particular center here. This is how I would kick out that fragment. The last one in the end is nitrogen, but it doesn't quite look like it has a diene structure. There's clearly nitrogen. What's missing, or what's weird about how it's drawn right now? Basically, your double bonds aren't in the right positions, right? Normally, if I were to draw this out, and said that here is my diene, carbons 1, 2, 3, and 4. Notice we don't have a double bond between 1 and 2 and 3 and 4. That's just a consequence of which resonance isomer of your benzene, basically, you've drawn, right? You can redraw this. This same structure could be drawn as nitrogen, nitrogen here, my CF3, and chlorine, where the double bonds are just located here, here, and here. In that particular resonance isomer, it's much more obvious now that you can see carbon 1 and 4, there's my diene. Nitrogen already has a double bond, which means when you do your cycloaddition, you're making your nitrogen triple bond, which would come out of it. So this is one of the things that can sometimes hide, is if you have these already aromatic type starting materials, you have, remember, 2 different resonance isomers there. In order to really visualize it, you may need to draw a particular resonance isomer of 1 and 2, 3 and 4 in order to give you the proper sort of geometry. But anyway, how these all work is you're always going to be extruding some type of molecule of gas, where again it's nitrogen here, CO2 here, or SO2 here, as a fragment. These are very useful ways of doing it, because what you're doing is effectively fooling the reaction into making this bicyclic structure, extruding a gas, and you end up locking in your product. So let me show you how this molecule works. So I'm showing you with this one. Each of those particular precursors has a very similar mechanism. I'm going to give you an example based on this SO2 extruding system. So first, let's identify our centers, carbons 1, 2, 3, and 4, carbons 5 and 6. Now remember, It's symmetric, so we don't have a problem of regiochemistry. It doesn't matter which way we position them. The methyls on the dienophile and your diene are all symmetric, so there's no top-bottom. We can basically pick any point. We could come in from the top or from the bottom. Those will give you two different enantiomers. What do you think we're going to do here? Just based on how I've positioned it, where the methyls are actually pointing back towards the ring, I'm starting from what could probably be the exo or endo pathway, which is this. If the methyls are pointing back and basically coming in underneath the ring, what do we call that? If the methyl groups are tucked underneath my diene, that's which? Is that exo or endo? That's endo. It's underneath the double bond of that ring. So if I were to draw my mechanism, 2 electrons, 2 electrons, 2 electrons, 6 electrons altogether to make my cyclic system, I'm going to form, because I've got this bridge, I'm going to draw it in this bicyclic kind of shape. So to number them off, carbons 1, 2, 3, 4, 5, and 6. I'm going to have at the top an SO2. Actually, let me draw out the atoms like this. So it's capping off. We're making this Norbornene-like structure, this the 2-2-1 kind of bicyclic system. And the two methyl groups are actually underneath or pointing down into the ring. That's because we've got the hydrogens here out and away. The hydrogens are in the exo position. The two methyls will be in the endo position when we do this. So that's just showing you this geometry in this way. If I was going to look down in sort of like a line bond version of it, I would have a 6-membered ring here, carbons 1, 2, 3, 4, 5, and 6. Let me put them over here, 5 and 6. The methyls would be dash, and I'm going to have an SO2 sticking kind of bridging off the top this way, like this. So it's capping over the top. If I was viewing that bicycle from the top, what I would have is these two methyls back into the plane, the sulfur sticking up from the top, as imagine if you're looking down from the top of the structure. That's my intermediate. It's stable, you can form it, but this is not the end of the product. What's nice about this system is I can go through one more reaction, I can extrude my SO2, and by doing that, I no longer have that gas present, I've locked in that molecule as my final material. So how that second step happens is by another 6+2 or 4+2 cycloaddition. Think of it like a retro Diels-Alder at this case. So it's going to involve double bond over, these electrons going onto the sulfur. We have to break that sulfur to carbon bond or whatever the gas fragment is. We're going to break this one. And we take those last electrons and dump them back into here. So what we're doing is a pericyclic reaction in this plane. Over here, it would look like this. Here, up onto sulfur, down onto here. So again, what we're doing is we're populating electrons between carbons 1 and 2, carbons 3 and 4, while we're fracturing the bonds, the carbon-sulfur bonds on both sides. So the product we get from this is going to look like 6-membered ring. I'm not touching my two methyls. Those will still both be down, like this. If we number it off, it's carbons 1, 2, 3, 4, 5, and 6 over here. What's the bonding geometry? 1 and 2 and 3 and 4 both have what now? Double bonds. Yep, we're going to have a double bond here and a double bond there. So we end up reforming this diene as a result of this. We're also kicking off SO2 as a gas. Yeah?
The fluorine still exists in this.
Oh, yeah. Sorry. Fluorines are, bloop, oh, crap. Fluorines are here. Fluorine there, fluorine there, fluorine there, fluorine there, and likewise, fluorine, fluorine. They're just carried forward at that point. So, good copy looks like this. So it's a two-step process. Cycloaddition to install your new carbon fragment. Here we're expanding the 5-membered ring into a 6-membered ring. I'm showing you both geometries, either from the top line bond or from this kind of house, the kind of chair type perspective. And again, this is just assuming it went endo, where the methyl group was underneath that ring. Remember, that's our kinetic product that's generally going to be favored. After this, though, the cycloaddition is this pericyclic reaction, so 6-membered transition state to go in, it's a 5-membered transition state coming back out, but you still have 6 electrons moving through it. You end up having this, and that's only a consequence of this 5-membered ring. Go through and practice the mechanisms for each of these ones. So I've shown you this one. Likewise, the same general theme is going to work across those other two, the CO2 extruding and the nitrogen extruding. Both of these can change. Like basically what I'm trying to show you here is the gas molecule you'd extrude, SO2, CO2, and N2, those are fixed. What you decorate on carbons 1, 2, 3, and 4, those can change. Now generally, because these are usually inverse electron Diels-Alder reactions, they will be electron withdrawing groups. But for example, instead of 2 fluorines on my SO2 extruding one, I could have 2 iodines, 2 chlorines, 2 CF3s, an iodine and a CF3. Those are my payload that I can change up. Likewise over here, these pieces could change. I can decorate anywhere on that part of the ring and they still become a nitrogen extruding reaction. Yep.
When you say that the gas groups are fixed, like, do you mean like they have to be in like fixed locations on molecules?
Exactly. Basically what I'm saying to you is the main template is the nitrogen extruding Diels-Alder bit will always look like this, where you've got different substitutions here, but I'm always going to have this 4-membered ring, aromatic, with a nitrogen baked into the core of it. That's always going to be my nitrogen extruding core, basically. Make sense? Again, super cool way of doing this. This is how you make specialized things. Like in this example over here, you can see what we're actually doing is forming a benzene. And if you go back to what we talked about for like Friedel-Crafts alkylation, Friedel-Crafts acylation, instead of going through and taking benzene and decorating around it, this is your first way of actually forming a bespoke benzene of your own. You're actually making the whole aromatic reaction. So go through this one, follow the mechanism, see if you can work that one out. So that's the end of Diels-Alder. The next 2 cycloaddition reactions, very similar. Instead of using only pi bonds, we're going to talk about what are called sigmatropic rearrangements. The difference here is instead of only pi electrons doing some type of a cyclic transition state, now we're doing a combination of pi and sigma. So the sigmatropic rearrangement, what we're doing here is, notice, it's 2 pi bonds and a single sigma. And what we're doing is we're migrating that sigma bond across the entire system. So this hydrogen starts off, if I number it, carbons 1, 2, 3, 4, and 5, turns into carbons 1, 2, 3, 4, and 5. You're fracturing that carbon-hydrogen bond, the sigma bond between carbon 1 and the hydrogen, and you're donating it over into carbon 5. We're sliding it over on the other end of the ring. Now, in this unfunctionalized case, would the name of the molecule, starting material, and product be different? If I had to use the IUPAC name of those molecules, is there any change? No, these are the same thing. So this is a reaction that normally you would never even see it happening unless there was a functional group. If I had something over here in carbon 2, now you would see that the hydrogen relative to that functional group, hydrogen relative to the functional group, has changed. So this is only visible when we have something where there's some actually functionalization. Right now, this is what we would call an identity reaction. If we don't have any functional groups on here, there's no way to know that this is happening. This is just the electronic pattern that's going on. So how this works, the notation is a little bit different than we talked about before. This is what's called a 1,5 sigmatropic rearrangement, where the numbers here represent the atoms that are involved in this shift. So the 1 refers to I have a single atom which is moving between carbon 1 and carbon 5, effectively. You're jumping over from this one. So this notation of this, what we call a standard sigmatropic rearrangement, you can have different ones that follow this pattern depending on how extended the pi system is. So what you've represented over here, this is a sigmatropic rearrangement where the sigma bond goes from carbon 1 to carbon 5, and we give it the notation of a 1,5 sigmatropic rearrangement. Again, very similar to the overall orbital overlap. Only difference is we're actually going to be making a what you call a new product as a result. Now, if you had to give this a numbering scheme, look at how you're forming here. We still have 2 pi bonds. We have 1 sigma bond. If I was going to draw the electrons here, it's still 6 electrons. I might draw it like in this direction like this. That's where I'm forming and breaking bonds at these 2 edges to make this one over here. So if I had to give this a numbering one, how many atoms are moving and how many atoms are sliding by? So this is not a 1,5 anymore. This is what? What might you call this? Somebody give me a shot. What do you got?
Maybe a 1,3.
A 1,3. How many atoms are moving overall? So we are moving a payload of 1, 2, 3 atoms over a range of 1, 2, 3. This is a 3, 3 sigmatropic rearrangement because 3 atoms are moving 3 atoms away. We're doing this end-to-end flip. So this ends up being a 3, 3 sigmatropic rearrangement. So the patterning you're looking for, again, for these kinds of reactions, 2 pi bonds and 1 sigma, and if you're getting in this type of transformation, once again, as drawn, it'd be difficult to see this one is happening because the IUPAC names of the 2 products, starting material, don't change. This is something that is obvious when you have a functional group which allows you to see that transformation. So this is what you're going to try later, what you might call this one in terms of numbers. Remember, you're taking how many atoms are moving, that's your first digit, and the second one is how many atoms are sliding along. So talking specifically about this 3-3 sigmatropic rearrangement has a special name because it's called the Cope rearrangement. It's a very, very useful reaction because it allows you to almost do molecular origami. Right? This is not the same thing of like our carbonyl functional groups we've been doing. We have to rip off protons, make a nucleophile, make an electrophile. The reason these reactions are so important is because we're not dealing with anionic centers and like classical sp2 and SN2 type chemistry. Remember, because they're involving pi systems and pi overlap, we have all the goodness of having that molecular geometry enforce a certain type of product. It allows us to take a reaction that has a certain shape of my molecule and certain functionalization and give me stereocenters as a result of the molecular orbitals that we have. Now, in a molecule like this, does this reaction, which side of the equilibrium is favored if I drew it like this? There is no side, right? This is identical because the energies in the starting material and product must be the same. It's the same molecule. So what would the equilibrium constant for this be? Is it going to be bigger than 1, smaller than 1, or equal to 1? Better say equal to 1. We're in the last week of classes. Equal to 1 should be the only thing we get. The capital K is 1 because the energy, the delta G of this system is 0, right? We're not going anywhere. That's where what we do to actually use these usefully, these are the 3 patterns that uses what we would call a useful Cope rearrangement. So in the first case, we're going from a molecule where if I draw out my reaction, sigma bond slides over, pi bond slides down to make a new sigma bond, pi bond hops over. So we're still going from 2 pi and a sigma to 2 pi and a sigma. That's what we're showing over here, where we get our new pi bonds and a new sigma bond as a result of it. Now, in that first example, starting material or product, which is more favored? Starting material, product. Who says starting material? Who says product? Why product? What's better about the products? Yeah.
Because usually like R groups can be larger, so standardly they're farther apart and it can migrate more.
Yeah, that's not too bad. You imagine if you make that one, you've broken that bond between the 2 R's, they can now rotate away from each other so you could get sterics out of the way. That's good. There's something else about your double bonds. Which double bonds are more stable? Yeah.
They're now like R's attached to the sp2 more.
Well, there's still sp2s, but the big difference is you are going to a di-substituted alkene, and you have a mono-substituted alkene as a starting material. We're going to higher substitution patterns, right? Over here, this is a mono-substituted alkene. These are now di-substituted alkenes. So this is back to the general rule of thermodynamics says higher substitution patterns in our alkenes will be more stable. So yeah, sterics is a big point, getting those 2 R groups away from each other. That's another good one too, as you can imagine, if I start off with the molecule in my starting material of A, as soon as that reaction happens and the bonds can actually rotate away from each other, getting back is a lot harder because now they have to rotate back. You have to get to a conformation where the thing's folded in back on over itself. It's much harder to do that. So that gives you a driving force where if I can make that starting material, heat it up, I can pop over to that product. And it's going to be enforced in this geometry too, where you have those 2 trans alkenes. Really, really useful. Try to do that by like SN2 and elimination. I dare you. Next one, B. Once again, there's my reaction. Now notice I went one way or the other way. Counterclockwise or clockwise for your pericyclic does not matter. It's a circle. You can go in either direction. But it is going to be concerted. When we do this, we end up with 2 pi and a sigma becomes 2 pi and a sigma. But what do we call this functional group? Everybody in one giant creepy voice. This is called a, there you go, Enols like to, this is called a what? Tautomerization. We go to a tautomerized product because enols are not as stable as their keto-enol form. What you're doing is you're locking over that bond. As soon as you do that, it's no longer a 3,3 sigmatropic rearrangement. I have to go back to my enol to get back to my starting material. So this is very, very, very product favorite. This is what we call an oxy-cope. It's a really, really useful molecule because what you're doing is you do the sigmatropic rearrangement, it makes this enol product, and then, tautomerization makes that product disappear, right? The intermediate slams over all the way to the right. So then you get very, very good favorability for this guy over here. So this is product favorite, as is this one. Last one down here. Once again, I'm going to go this way. 2, 2, and 2 makes my product. Now notice I've made here, when I draw this one out, I have made a new bond here. If I number these off, this is 1, 2, 3, 4, 5, and 6, which corresponds to 1, 2, 3, 4, 5, and 6. So I've got a new bond, sigma, between carbons 3 and 4. Notice I've fractured a bond between 1 and 2. That's gone. There's now double bonds between 1 and 2 and 4 and 5. And I've made what? This is how big of a ring? This is which is allowed, by the way. If I say it is, you can make one. Ha, ha, ha. But what's happening here? Why is this driving to your product? What's helping it out? Yeah, ring strain, right? You're taking a cyclopropyl ring. This is a very, very strained ring right here, and you're relieving that ring strain by opening it up into a 7-membered ring. Again, it's going to end up with the same geometries. You still have these cis kind of sisters. You're also making higher substitutions. Monosubstituted become disubstituted, but this is really, really favored because of that ring strain. Going back is very difficult because you'd have to form a new strained ring between 1 and 4. So this is how you use the cope reaction usefully. It has to be substituted in a way that one of the side of the equilibrium is going to be favored because of energetics, substitution, or electronics. So let's go through this mechanism. If this was your molecule, I'm showing it extended, and we're going to go through a cope type reaction, sigmatropic 1. How does this work out? Step 1, if you're doing a sigmatropic arrangement, and again, the main thing with all these reactions, big clue, you take a molecule, you beat on it with heat, that's all. That's a real clue number 1 that you're probably doing just a sigmatropic rearrangement. Also, nothing else. Just starting material and heat gives you that material, right? So if you're looking for a reaction like this, and this is like what the heck happened, one of the ways to test this is you're not adding any other reagents besides molecule, conformations, and heat. So as drawn, we have 1, 2, 3, 4, 5, 6. Now notice you've got a double bonds at both ends and the sigma bond in between. That's a hallmark of something that looks like a cope rearrangement. We just have to redraw it in a geometry where this becomes obvious. So I'm going to draw it in my cope, and I always remember this where it's C for cope. Makes sense? So you draw it in this cissoid type structure. Once you've got it set up, I'm going to have a double bond at both ends, and I'm going to number this off as carbons 1, 2, and 3, 4, 5, and 6. Where notice carbon 4 has a gem dimethyl associated with it. That's it. That's my substitution pattern. Now that I've got it set up in that geometry, I can do my rearrangement, double bond over, single bond down. Now I have no more batteries. Oh well. We will continue. So now we're going to end up with the C facing the other direction. Again, whoops, numbering these off, this is carbons 1, 2, 3, 4, 5, and 6. Where you have a new sigma bond between 1 and 6, you've got a new pi bond between carbons 4 and 5, new pi bond between carbon 3 and 2. It just happens that carbon 4 has a geminal dimethyl attached to it as well. So if we unfold this, that should give you this molecule over here. If we're numbering these off, this is now carbons 3, 2, 1, and carbons 4, 5, and 6. With a new bond there between 1 and 6. Make sense? So this is something where if you walk through this, numbering out your 1, using your color coding and stuff really helps you with for where these geometries go. So I'll go through this one after. Similar kind of structure where you have a molecule that's set up. This is where we're forming, again, a Cope type reaction, and just draw out the product and mechanism for this one. Next one is called the Claisen rearrangement. Similar sigmatropic reaction. The only difference with this one is usually it has a heteroatom in the backbone. That's just one of the major components. The second one is most Claisen reactions actually start from phenols. We're actually using this as a way of temporarily interrupting aromaticity in order to make our product. It's another really good way of actually making ortho-substituted products. This is an example of how to make something that normally trying to do this by Friedel Crafts might be a nightmare. So what you can do is start for the phenol. With your phenol, you can append this group, and then we use the rearrangement to attach something onto the center to give us these allyl substituted phenols as our product. This is a really useful reaction for attaching a pi fragment and then using this allyl substitution to slide that over into our product. So how it works, again, electrons here is very similar. We're doing sigma bond up, pi bond down, pi bond over to give us our products over here. Now, if you look at these two on the top, if you looked at it and said that, okay, well, which is going to be more favored, we're going from an enol-like structure to a aldehyde-like structure. There's already an energetic bias here to make us, instead of forming this enol-like one, we're making a carbon-oxygen pi bond, which is generally a little bit more stable than a carbon-carbon pi bond. So already in an acyclic form like this is going to be more stable as your product. That's already helpful. The really good application, though, is the one I'm showing you at the bottom. What I'm showing you here is this is a labeled carbon. That's a carbon 14 label. And what we're doing is, again, sigma, or 246. That's forming a new bond right here, and we make this keto structure. Now, normally, notice what we've done here. Temporarily, we just broke aromaticity. I took phenol. I borrowed the pi bond for a second. I've slid it outside the ring. I've made a carbon-oxygen double bond, and I've put an sp3 center inside the ring as a result of that. But because I've done this, I've been able to attach this carbon to this ortho site. So again, this is really useful because I can take a phenol, I can append this allyl group onto it, and I can stitch it into the ring only in the ortho position. There's no para at this way. It's just an easy way to go a single substitution, bouncing from oxygen over to my carbon. What makes this possible, even though this is a very high energy intermediate, I can re-aromatize the system by, once again, starts with the T, it is your tautomerization, right? We're going back from a keto to the only stable enol-like system. So I'm moving this hydrogen back, which regenerates my sp2 center, regenerating my aromatic system. So that's what gives me my driving force of the reaction. It's pretty hot. Like usually this reaction, uncatalyzed, has to happen about 200 degrees. This is something that's being done in like a microwave, something at very, very high thermal promotion. But again, very useful reaction to use in this way. And it's 2 steps. You would set up by starting with your phenol, add in your allyl group, high temperature, punch it over, there's your product. Yes?
Why did you say the aldehyde is more stable than the
Remember, what you're talking, from your starting material, you're talking about this one right here, right? The constituents of that molecule is 2 carbon-oxygen sigma bonds, 2 carbon-carbon pi bonds. In general, a carbon-oxygen pi bond is worth more. It's lower. It's a better exotherm to make than a carbon-carbon. So I'm swapping a carbon-oxygen sigma for a carbon-oxygen pi. It's the same thing as looking at the enol versus the keto. Generally, we say the keto form is more stable than the enol because we're swapping a carbon-carbon pi bond for a carbon-oxygen pi bond, right? Again, just a little bit this side, but again, practically, this is how you actually use the cope, is where you're tying it to aromaticity as well. Make sense?
Does this apply to all carbonyls?
Yes. Every carbonyl. That's why, look at the keto-enol tautomerism, right? A keto form generally will be more stable because you're gaining a carbon-oxygen pi at the expense of a carbon-carbon pi, right? Unless we've got something like the phenol where we've got other components. Okay. So let's go through the mechanism of this one, drawing the product through here. If you start off with a molecule like this is your Claisen rearrangement. So numbering it off, this is carbons 1, 2, and 3, 4, 5, and 6. Take a second, go through this, see if you can draw out your product. So we've presented this right now where those double bonds are actually lined up. You know, one of the complications of a molecule like this or reactions like this is if the conformation doesn't immediately show as your sort of cope-like structure, it can be difficult sometimes to see what the transformation is. This is why if you see a molecule like this, where you've got 2 pi bonds, like an enol-like structure, only heat, start thinking this is a sigmatropic rearrangement. It's probably what you're looking at. Again, that's that core pattern. We're showing it here in the middle. So how this one works, I'm going to have electrons over, electrons down, and electrons up. I'm sliding over my pi bonds. I'm making 2 new pi bonds, a new carbon-oxygen pi, a new carbon-carbon pi, and a carbon-carbon sigma, where I'm breaking a carbon-oxygen sigma. If I draw out the structure, first thing to usually do is try to maintain the atomic position. So I'm actually going to draw out the first half in the same kind of geometry, where we have carbons 1, 2, 3. Down here we have our oxygen, and then the 5-membered ring attaching down over here. So this is 4, 5, and 6. We have a new bond between 6 and 1. We have a pi bond here and a pi bond there. So the geometry that we started off with, that's why we end up with a trans geometry between carbon 3 and 2. We also end up with our ketone being formed here. And you can actually unfurl that or draw it out where this is extended. And you get a structure that looks like this. So there's one more for you guys to try it later. Here's a molecule that you'd be doing a Claisen rearrangement on. This is an example of something where if you try to do this one, the allyl actually has to go around to the para position down here. See if you could work out the mechanism for doing this. This is a unique case where it does not put on the ortho position. It actually slides around to para. Okay, guys, I will see you on Wednesday. Okay, so for these problems here, we're doing a gas extrusion inverse electron demand Diels-Alder reaction. If you look at those 2 materials, this is our dienophile, making that our diene. And based on the ones we discussed today in class, that's the diene fragment. So this is carbons 1, 2, 3, and 4. Notice this is our CO2 extruding reaction we have built in here. So let's focus on those 2 parts. So if we're going to number this off, the carbons we're looking at is carbon 1, 2, 3, and 4. And that makes carbons 5 and 6 here. If you go to your product here, just looking this out, remember carbon 2 has our ester attached. This is carbon 2 here. The other 2 carbons 5 and 6 are on the other half. So I would probably number this off as carbon 1, 2, 3, and 4, making this 5 and 6. So these 2 here, or this segment comes from your dienophile, and these ones here come from your diene. So the electron, or the mechanism for this one is going to be 2 electrons over, 2 electrons, let me redraw it like this, 2 electrons up, 2 electrons over, forming a bond between carbons 4 and 5, and 2 to the back over there. So that's the sequence. And notice we've got this bridging structure here. So what it's going to look like is our 4 carbons across the back, our 2 new bonds that we're forming, and then the electron, the 2 carbons 5 and 6 sitting off here. So in fact, when we do this, we're going to be reducing this from an alkyne to an alkene. So this is carbon 6 and 5 shown here with our 2 methyl groups attaching. Going back over here, let's say this is carbon 1, 2, 3, and 4, which means carbon 2 over here and carbon 3. Between carbon 2 and 3, there's going to be a double bond. That's what we're forming across this. And then on carbon 2 is our O-methyl, like that. Which means now we still have to have this bridging structure. The bridging structure is going to bridge from carbon 1 to carbon 4, and that's going to go up, oxygen, over, down, carbonyl. So that's the sort of the bicyclic intermediate we form. And then from there, we're going to do another Diels-Alder reaction. So that's going to be up to make a new bond between the 2 oxygen and carbon. Down, we're making a double bond between carbon 3 and 4 again. And we're sliding this pi bond over between carbons 1 and 2. And that's going to give us our final structure. Granted, the resonance structure, the exact positioning of our double bonds in this benzene don't quite line up, but remember the specific one, if I was to draw this off based on our positioning, let me just finish this off. It will look, there's our 2 sigma bonds, and here's our backbone. There are 2 methyls, just based on how I've drawn it. We're going to have a double bond here and here. This is carbons 1, 2, 3, and 4, and down here is 5 and 6, where again carbon 2 is going to have our O-Me. So that's our final structure, where again you can do the sort of the pancake flip or a resonance where the double bonds inside the benzene ring may be in different physical positions. Okay, for this sigmatropic rearrangement, what we're asked to do is designate it in terms of its numbering. So this would be described, if you go over here, we have a single atom which is sliding across a 3-atom system. So this is a 1, 3, or 1, 3 sigmatropic rearrangement. Again, the 2 ways to see that is this 1 atom is sliding over to carbon number 3, so 1, 2, and 3. It's now bonded sigma to carbon number 3. Also in the transition state we have here, if we were to fracture those 2, we have an isolated 1 carbon and a 3 carbon fragment over here. That's why we're giving this designation of a 1,3 sigmatropic rearrangement. Now, if we're going to draw this one for a cope rearrangement, again, that's going to be the pi bond is going to come over, pi bond is up, and over here. So this is a total of 1, 2, 3, and 4, 5, 6. This is, remember, a 3,3 sigmatropic rearrangement. So when you draw this out, again, I'll just draw starting out with the sigma skeleton kind of in the same general position. We have a 5-membered ring attaching over here and 5-membered ring attaching over here. So we have a double bond here and a double bond over there as a result of it. And again, what we've done now is we formed this ring. We've got a higher substitution pattern, so generally this side is probably going to be more stable. All right, so to talk this one through, we're doing a Claisen rearrangement. Remember, this is a 3,3 sigmatropic rearrangement where the double bond is coming up here to make this carbon-oxygen double bond. We're going to slide over the sigma, and then this one is going to be coming down over here. This is, if I'm going to number them off, this is carbons number 1, 2, oxygen is 3, 4, 5, and 6. So the 6-member transition state we're going through here. Now, what that's doing is that's interrupting the aromatic ring. We're moving the double bond between carbon 1 and 2 out. So let me just redraw those 2 parts. So just keeping it in the same sort of geometry we had. We've got like this. The oxygen is now going to be double bonded. And we still have a methyl, and now the sigma skeleton is attaching the allyl group over here. So that's, I'll draw it out as like this, where we have carbons 1, 2, oxygen is 3, and then over here this is 4, 5, and 6, where now we've made this new sigma bond over here. Sorry, that was a atom number 1 right there. So we still have this sp3 center. Normally, the Claisen reaction would stop right here, but we can't re-aromatize. There's no proton on carbon 1 because we have this methyl group over here instead. So the reaction's still under high temperature. What we have to do is find a way to get back to aromatic, and what you can see now is just renumber this across a new numbering system. So 1, 2, 3, 4, 5, 6. If you look at that, that is now a cope effectively. What we have is a 6-carbon system where we have a double bond in one end, double bond in between, and the sigma bond in between these two. So we were set up to do a cope rearrangement where this can go, we can take double bond and slide it over here. This is going to slide up and this down over there. So that is now going to give us a new intermediate. We're not done quite yet, because remember there still is a hydrogen over there. So we're going to have something that looks like this, methyls at those two positions. We still have hydrogen over here, and we've just taken this 3-carbon fragment and walk it down one more time. So we're going to have sigma 2, 3, like that. And then using the green numbering system, this is atom number 1 is here. It's the one that is now attaching to carbon 6. This is carbon 5 and carbon 4, and 1, 2, and carbon 3. Carbon 3 over here used to be attaching to that position, but we've done this another sigmatropic rearrangement to get down over here. Now we're in a position where we still have this hydrogen. We can effectively undergo tautomerism. This is basically, think about a base. Might grab this one and allow us to slide these over where we pick up a proton on this side. So that'll get us through to our final compound, which is now re-aromatized. We've got our aromatic ring back, our methyls in those positions, our OH, and we're going to have our allyl fragment sitting down over here.